Assalamualaikum, my name is Muhammad Arunas from Group A and I would like to present our group project. So this is my group member and our project is about creating a good machine learning model for slum concrete dataset. This project is related to SDG 9, Industry Innovation and Infrastructure, and SDG 11, Sustainable Cities and Communities. The problem that we have found is that the importance of concrete mixture design is critical for the construction industry to ensure performance and durability of concrete structure. This rely on empirical method and intensive laboratory testing, which are time-consuming and resource-intensive. So we offer faster and more accurate prediction, hence efficiency and effectiveness in concrete mix design. Our objective is to create model for predicting concrete slump flow and comprehensive strength based on its component to evaluate the performance of different machine learning algorithms including linear regression, SVM, neural network, and random forest. This is to provide insight into the relationship between concrete mix component and their output. And I will pass it to the next presenter. Thank you.
So in our data analysis, we use our dataset that we found in data.world. In the dataset, we have 103 columns with 10 features, and the dataset is about the composition and properties of concrete mixtures. We have cement, we have slag, fly ash as the columns and the attribute name. And we process this data before we feed it in our model. We do the data cleaning, we do the normalization and principal component analysis. And for the data cleaning, first thing and foremost, we initialize the target features. So we select the compressive strength as the target features, as this will become the prediction value for this whole project model. And then we initialize the trend split test. So this is the data processing so that we can recall the trend split test in many models and that we'll be using in this project. And also we will be using standard scaler so that we can scale the features so that we can scale the different scale that disproportionately influence the model. So this is ensure that it contribute equally to the model decisions. So we check the missing values. As you can see, there is no null values. We check the rows uniqueness, and also we check the duplicate rows. Then move on to the data visualization. We plot a heat map. So this to visualize the importance of different features and relationship between the features. And this is also how we want to find the attributes that is highly correlated. As you can see, slump and flow is very highly correlated, and we might want to drop it in the future. And we also plot seaborn. So this seaborns is just to visualize the statistical relationship, just to show the distribution of data and to visualize the linear relationship between each features. And also this box plot, this is to identify the outliers of the data. This to show the individual points outside the whiskers, and this help understanding the spreading and any unusual data points that may need for the investigation. Okay, and like from the previous heat map, we decide either flow and slump. But as you can see here, when we feed it in the random forest regressor, we see that the mean squared error for feature flow is much lower compared to slump. So this means that we need to drop flow because it is much lower MSE compared to the slump.
Alright, now I will be presenting about our first model, which is linear regression. So first of all, we have to create our linear regression model and train the model. Next, we have to do predictions using the testing set and evaluate the model using mean square error. So our result is 4.45, and this is the actual versus predicted graph. So we want to improve the mean square error by adding some method like principal component analysis. So when we do the principal component analysis, we got 4.688. So the mean square error with the principal component analysis is slightly higher than the model without principal component analysis, which is 4.45. So we decide to not use the PCA further in this model. So next we try to perform RFE, recursive feature elimination. So we adjust number of features to 5. So among all the features, we only choose the 5 most important feature in our dataset in this RFE method. So we do it with the linear regression and without the PCA. So the MSE that we get is 4.21 or 4.207, which is good, which is better compare compare from the before. So we maintain the RFE method in this model. So the features that RFE method choose is cement, fly ash, water, coarse aggregation, fine aggregation. So this is the 5 most important features in our dataset. So after the RFE, we perform the regularization using the lasso. So in this regularization, we do the has a parameter lasso alpha 0.001, 0.01, 0.1, 1, 10, and 100. So we choose the best combination using the grid search and the MSE method, and the MSE result we get from the cross validation is 0.759, and the best parameters is lasso alpha with the learning rate 0.01. So so the with the best model that we got earlier, so the mean square error is 0.489 with lasso alpha, learning rate 0.01 with poly degree 2. So in this model linear regression, we improve the model by using RFE with the grid search and regularization. And we got the final score, which is 0.489. So the second model we chose is neural network. So in this neural network, we use the activation. First of all, we train the dataset using the TensorFlow, and we define the neural network model with activation ReLU, and each activation has their respective dense. For example, first 64, second is 32, and activation linear is 1. So next, we compile the model using the optimizer Adam and loss with a mean square error. And this is early stopping. Early stopping means when the changes is no longer there, the the model will stop running. The neural network will stop running. So we train the model and evaluate the model using mean square error, and we can see here the number of epoch is 100 and batch size is 32. So it will run 100 times, and the mean square error that we get in the end of the running time is 42.7. So 42.7 is quite high for the mean square error, so we try to perform PCA alongside with the neural network to see whether the MSE can be better or not. So after we apply the principal component analysis alongside with the neural network, we get about 60.777 for the mean square error. So we thought that it will reduce the mean square error, but it got worse because it increased significantly from 40 to 60. So we decide to not use PCA in this further model, in this neural network model. So after that, we try to find the best combination of hyperparameter using the loop. The reason we are using the loop because we have tried to use the grid search, but there is a slightly, not a slightly, but there is an error from the packages. We don't know how, we don't know why, and we don't know how to fix the issue. So we choose alternative solve, which we are using loop. We are using loop to identify the best combinations of the hyperparameter. So in this hyperparameter, we have Adam, we have SGD and RMS prop. And for the learning rate, we have 0.001, 0.01, and 0.1. So after the loop, we can see that the best parameters is with the optimizer Adam, and learning rate is 0.01. And the MSE we get is 17. So that's
So, Assalamualaikum. So now we will be exploring random forest regression, a powerful ensemble learning method. So we will walk through the implementation process, examine the impact of PCA for this model, and see how hyperparameter tuning can enhance our model performance. So let's start with the basic random forest implementation without a PCA. So we use 100 trees in our forest without any optimization. We achieve, let me run this first. Okay, we achieve 9.37. This baseline performance give us room for improvement. So let's see the plot. So this scatter plot shows the actual versus predicted values for the initial random forest model. So the point generally follow the red dash line, indicate it's a good fit, but however there is some scatter, especially at higher values, suggesting room for improvement. So let's explore PCA. Exploring PCA for dimensionality reduction. Is it worth it? So we investigate it. How PCA could improve our model. We tested PCA with different numbers of components from 1 to 9. And so interestingly, we found that, wait, let me run this first. Okay, so interestingly, we found that PCA actually increased our MSE in most cases. So the best result with PCA use 7 component, which is 10.30. So the first one is 9.37. But if we added PCA technique, we will get the best one, which is 10.30. This is slightly worse than our baseline model without PCA. So based on this result, we decide not to use PCA in our final. So we can see in the plot show how MSE changes with the number of PCA component. So it decreased rapidly from 1 to 4, uh, and then fluctuate before reaching its minimum, which is 7. After 7 component, the MS is slightly increased, so suggesting that 7 is optimal number. But however, it's still, even at its best, PCA doesn't outperform our original model. So let's move on. We are using PCA with 7 component, and it's still, you can see the graph here. is still 10.30. It's slightly worse, so yeah. So let's move on. So we are using the data without PCA. Now we are tuning it, hyperparameter tuning, using grid search. So we search through various combination of n estimators, max depth, mean sample split, and mean sample if. So let's run this. It may take a while, a little bit. So let's see. So now this is what we got, the best hyperparameter with uh, n estimators 150, max depth none, mean sample lift 1, and mean sample split 2. So with this optimized parameter, we achieve our best MSE, so which is 8.75. So let's see this graph. This so maybe this setting allow for complex tree and a large forest. That's why it takes a while to do it, to run the code. So it may suggesting that the data has intricate patterns. So the resulting MSE is 8.75. So maybe it can be improved. So there is an improvement over both the initial model and the PCA model. So let's compare the result here. Let's run this one. Okay, so we can see that basic random forest, which is 9.37 if I'm not mistaken. Random forest with 7 component, which is 10.3, and random forest with hyperparameter tuning, which is how much, 8.75. So as we can see, the hyperparameter tuning provide the best performance, while PCA actually decrease our model accuracy in this case. So we've seen that random forest can be a powerful tool for regression tasks in conclusion, but PCA isn't always beneficial. In our case, it slightly reduce the performance. Hyperparameter tuning can significantly improve the model performance. So our final model achieved MSE, mean square error MSE of 8.75, a notable improvement over our baseline. So that's all for random forest regression. Assalamualaikum warahmatullahi wabarakatuh. My name is Haris Nasrullah bin Suara Afzad. Now today we will be discussing about support vector machine, or that or support vector regression that we use. So support vector regression is a powerful machine learning technique for regression tasks, and we will walk through the process of implementing SVR, which is enhancing it with after that we enhance it with feature selection and dimensionality reduction, and finally optimizing its performance. So let's start with the basic SVR implementation. So let me run this first. Okay, so now we begin by importing necessary libraries and creating an SVR model. We train the model on our training data, make prediction on the test set. So we after that we evaluate the model using mean square error, and in our each neuron we achieve an MSE of 46.99, which leave rooms for improvement. So based on this graph, so this show the performance of the basic SVR model, the predicted values, y-axis cluster around narrow range 35 until 37. So regardless of the uh, actual values x-axis, so this indicates the model performance is very poor, as the prediction don't vary much with it with the actual values. So to enhancing SVR, we are using PCA. um, so we apply principal component analysis. So PCA helps reduce dimensionality while preserving important information. So we apply PCA with 5 components to our skill data. This reduce our MSE. So let's run this first. Okay, this reduce our MSE to 35.57, uh, a significant improvement. So we also achieve an R square of score of 0.297, which indicate that it is a better model fit. So in this image, we are using SVR with PCA. So after applying PCA, there is slight improvement, I guess. The predicted values show more variation, but the relationship with actual values is still weak because the points are more spread out. So, but also don't follow the ideal diagonal line closely. So let's move on. We are now we apply a technique called feature selection with RFA, recursive feature elimination. So we are using RFA to select most important features. So RFA helps identify and select most relevant features for our model. We combine RFA with PCA, and then this combination also dramatically improve the result. So let's run this first. Okay, and now we can see the MSE is decreased to 1.13, and the R square also increased to 0.978. So which indicates an excellent fit. So we can see in the image, this shows a dramatic improvement, very good improvement. The predicted values align much more closely with the actual values following the diagonal line. It's still more some scatter, but the overall trend is much stronger, indicate that a much better fit of the model to the data. So finally, tuning with grid search. So we are using grid search CV to find optimal hyperparameter for our model. We define the grid parameter. Uh, we define a grid parameter to search through. So grid search will perform an exhaustive search to find the best combination. So you see here we put kernel linear poly RBF or sigmoid. The C is 0.1, 1, 10, and 100 epsilon, 0.01, 0.1, 0.5, and 1 gamma scale or auto. So after that, um, we find the best parameter. Wait, let's run this first. It takes a while. Okay. So the best parameter we get C100 epsilon 0.5 gamma auto and kernel is RPF. So with this optimized parameter we achieve our best MSE, which is 1.09 from the first one, which is 46.99. We reduce it until 1.09. So let's see the image. So the final image show the best performance. The point align very closely to with the diagonal line, indicate a strong correlation between the final image, between predicted and actual values. So there are few outliers, but and the model appears to perform well across the entire range of values. So the conclusion, we can see how SVR can be significantly improved through PCA, RFA, and hyperparameter tuning. So this technique allow us to reduce our MSA from 49 to is it 1.1.09, a dramatic improvement in model performance. So that's for SVR.
So this part is the deployment part. So based on our result and finding, the mean square error for neural network machine learning algorithm is the most favorable one. So we take that into account and deploy the neural network model for our projects. So what we do is we use Hugging Face spaces. Here we create a web user interface where the front line we use the Streamlit, and here user can input 8 input values and then click on predict button. So here the input we have the cement, blast furnace slag, fly ash, water, sperm, glacier, cost aggregate, fine aggregate and flow. And then when we click on predict storm strength, it will give the concrete mixture a compressive strength in megapascal values. Okay. So the data processing has been done upfront, so that the model can use the data in ready. It can use the data in ready use, so that it also help minimize the resource consumptions and help the Hugging Face not offloading with the data pair processing competitions. So now the Hugging Face can simply load the data and focus on serving the model predictions without any data preprocessing step. So you can access our models from this link, and you can also look at its code from this file. So that's all for deployment. Thank you.
Next is the discussion of our key finding. First, the consistent superiority of non-PCA model implicate that original feature contain crucial information lost during PCA, suggesting dimensional reduction is unsuitable for this dataset. Second, nonlinear relationship that we have observed for superior performance of complex model neural network, rainforest, and optimal RBF kernel for SVM. Third, importance of hyperparameter tuning is critical for maximizing model performance and robustness of ensemble method that we have observed from the strong performance of random forest model even before extensive tuning. So the challenge and limitation that we face during doing our project is model tuning. Hyperparameter fine-tuning require extensive experimentation. Achieving algorithmal performance was challenging. The computational efficiency during training neural network and SVM was competition, and also large hyperparameter grid increased computation time. This balancing accuracy with efficiency is critical if you want to deploy. Next is data limitation. Small data set may limit generalizability. So, avenue for future work and improvement. First is the data acquisition. Obtain a more extensive dataset for enhanced generalizability and robustness. Second, advanced technique. Explore more assemble method and gradient boosting for improved predictive accuracy. Third, feature extraction. Create new data feature and explore domain-specific extraction technique other than PCA. Fourth, automated hyperparameter tuning. Implement Bayesian algorithm or genetic algorithm to streamline tuning. So, in conclusion, through our collaborative effort, we gained a comprehensive understanding of machine learning application in concrete property prediction. This project equipped us with valuable skill, knowledge, and insight, laying a strong foundation for future advancement and contributing to the ongoing development of this field. And that is all from us. Thank you.